Okay, so there are a few examples of source separation. One example is working in the time domain, single channel, or in the time frequency domain, but single channel, single microphone. Here I'm going to show you source separation of two speakers, but using audio visual, which means that we use a single microphone and video to track the lips. But it's possible to do different things. Maybe the light here, maybe, or I don't know if people see it clearly. Okay. Maybe to dim the light. Okay, so I'll show you a few examples like here. Note that, yes, this is good. Note that even though each one of them holds his own microphone, we don't use the signals in their microphones. Okay? So we don't use the signals that are received in their microphones. Then the problem is much easier to use these microphones. Even though each microphone receives the voice from here and also the voice from the interferer, but the signal to noise ratio using such a microphone is high. So it makes the problem easier. But we don't do that. Here we show an example of, we use just a camera and we use the microphone and the camera. And then we want to separate both of them. So here, all is when you listen to both of them using the microphone and the camera, single microphone and the camera. Here, we can move it here, so we can listen to this guy. We move it to here, we can listen to this guy. Okay, so let's see this demo.
I'm not a fan of flying. I hate being on planes. He might say, in general, there's so many noises. You know what I mean? I won't flush the toilet on an airplane because of the noise. Like, it scares me. You go, you hit flush, then you turn around, nothing happens for 5 seconds, then out of nowhere, boom! Boom! Oh my God! I just put a hole in the plane.
The city bus does not. It's terrifying. It is like a little UN meeting on wheels every time you get on it. We all walk through the same door. We all pay the same price.
Okay, so let's remove this one. Let's see another example. Like this, cafeteria.
Okay, so the task is, given the video, any person who you see talking, their audio gets cleaned up and everything else gets suppressed. Okay, so the task is, given the video, any person who you see talking, their audio gets cleaned up and everything else gets suppressed.
Okay, let's see another example. Just a minute.
He's not on a Danny Ainge level, but he's above a Colangelo level. In other words, he understands enough to... If I were a
You said it was all right to lose on purpose. You said it's all right to lose on purpose.
Yeah, of course
and
it is. It's called
advertise that to the
tanking.
fans.
Who doesn't know that?
It's perfectly okay. Don't explain it away now. Don't explain it away. You said it was all right to lose on purpose. You said it's all right to lose on purpose and advertise that to the fans. It's perfectly okay.
He's not on a Danny Ainge level, but he's above a Colangelo level. In other words, he understands enough to... If I were a Sixers fan... Yeah, of course it is. It's called tanking. Who doesn't know that?
Okay, so this... Okay, I don't know. Okay. You see in these examples that it's possible to separate, but it's not real time. It's offline. So it's recorded. So suppose that you see something, you record some video on your television or something like that, your camera, video camera, and you can process it in order to separate the sources. But it works offline using deep learning, audiovisual, and the complexity is quite high. But there are some methods that work even on single channel also. These kind of signals, even without the video, they work with deep learning because there are many parameters. It's much more difficult. So I encourage you to work on this example and try it, what we talked before. It will give you some insight. Any questions? By the way, here in the slides you have this paper, number 23. If you like, you can read it. And also on my website, in the journal publications, you have this paper and also a MATLAB code for speech enhancement. So you could try it. And actually it works in real time and also with signals, so you can play with it, you can listen to noisy recorded signals. Okay? Okay, so let's proceed. Now, after we talked about single channel in the time domain and single channel in the frequency domain, we move to multi-channel. So first we will talk about multi-channel in the time domain, then we will continue with multi-channel in the frequency domain. Okay, so if we have multi-channel, it means that we have more than a single sensor. We measure signals in multiple sensors. So we said that for single channel, we have the single channel model, and we will extend it to multi-channel model. So we will talk about the signal model, formulate the problem. Then we will talk about some mathematical, which is called joint diagonalization, or something similar. Sometimes we call it generalized generalized eigenvectors and generalized eigenvalues. So a generalized eigenvalue decomposition. You know about the eigenvalue decomposition we talked about before. So generalized or joint diagonalization, it's also very useful. And we will talk about it. We'll talk about the linear filtering and performance measures and optimal filtering matrices. And I will explain why we talk about matrices, which is also some kind of a generalization of the single channel signal enhancement. But if you are already, you know about single channel, you will see that the extension is much easier to multi-channel. So, okay. So let's start with the model. So instead of a single channel, now we have measurements. That each measurement, each signal that is measured in a sensor M, index M, is a combination of the desired signal, xm, plus noise signal in that sensor. Now we said that with a single channel, whatever is received here is the desired signal. But now we can assume that we have a desired source, and then we can take into account the reflections or the impulse response from the desired source to each of the sensors. Okay? Okay, so with a single channel, we assume that we have a measurement, yt, equals to xt plus vt. So here we assume that the desired signal is whatever is received due to the desired source in the single sensor. But usually, the source is somewhere in space. So here we have a source, desired source. And this sends wave, maybe acoustic wave, electromagnetic wave, whatever, propagating wave. This is the desired propagating wave. And this is measured by an array of sensors. So here we have Y1. We call it from 1, okay, 1, Y2, until we have Y and T. So we have M sensors. So here we don't need to assume that the desired signal is here. We can actually, each sensor received the source, the propagating wave from the desired source, convolution with impulse response, with a certain impulse response that takes into account all reflections from surfaces. And so it's not only delay, it can be impulse response that takes into account all the reflections from all surfaces, and then we receive the desired source component in the first sensor, in the second sensor, so on. So each sensor receives the source, including the effect of reflections, plus the noise in that sensor. And the noise in that sensor also, we can write it as convolution of some impulse responses from undesired sources, plus thermal noise, plus diffuse noise, plus any other type of noise. Okay? So this noise component is partially correlated between sensors. Here, the relation between sensor regarding the desired source is also given, something like that. Okay. So suppose that we know these impulse responses. It's a lot of information. If we know these impulse responses, it means that if we estimate, we can call this XMT. So this is the desired part of the speech that is, or the signal that is received in the sensor number N. So once we estimate any one of them, maybe X1T, or any one of them, if we know the impulse response from the source to that sensor, we can deconvolve. We can try to deconvolve and try to find XT. We can try to estimate XT from this set of measurements. And then we call it, to this task, we call it noise reduction or enhancement plus de-reverberation, because we try to estimate the signal from the source, the original signal from the source. So we call it de-reverberation or de-reverberated signal. So it includes both noise reduction and de-reverberation. But sometimes we say, okay, let's assume that one of the sensors that contains this impulse response is not the reflections are not that too significant. And it's mostly maybe a delay, like it's an impulse response with a delta, one impulse with a delay. Or maybe we don't care much about the reflections, about the reverberation. And in that case, we can choose one of the sensors, maybe the sensor with the least amount of reverberation. So this effect is the smallest. And try to estimate, let's call that sensor number 1. So we will estimate x1t out of this measurement. Okay? So we have two options. Either only signal enhancement, in this case, or signal enhancement and the reverberation, and we try to estimate the source from the noisy measurement, the noisy reverberant measurement. Okay? So in this lecture, I will concentrate on signal enhancement. But I want you to know that there are also problems that involve de-reverberation. I will not talk about it in this course, but those of you who are interested, I can give you something to read, a paper, so on, that try to do enhancement and de-reverberation at the same time. Some of you work on other tasks of signal enhancement. For example, image enhancement. So you are familiar with de-reverberation and noise reduction. You know that sometimes there is image reconstruction tasks. So you get an image, and the image is blurred. It's blurred because maybe there is a movement of the camera, or maybe a movement of the object while you're taking the image. So if the image is blurred, and you know the exact, what is called the impulse response in images, so it's point spread function, which is the impulse response. So if you know how the object is convolved, and then you get the blurred image, you can take the inverse, okay? So it's called deblurring for image, but it's the same, it's like de-reverberation. The problem is, deblurring, what will happen with deblurring? The noise will increase. So there are some trade-offs between noise reduction and deconvolution. If you try to do strict deconvolution, like this, if there is no noise, it's much easier. But if there is noise, direct inverse of deconvolution generates or increases the noise very sharply. As you are familiar, it's also similar that you know in mathematics. In mathematics, if you take the inverse of a singular matrix or a matrix with high condition number, which means that it's close to be singular, okay, even that it's not singular. So inverse of a matrix that with a high condition number, what will happen? Small error in the input. Small error in the input, what does it mean? Noise. Noisy measurement, small error in the input and the measurement will create high error, high noise at the output. Which means that after deconvolution, you increase the noise by a factor of the condition number. Okay? Those of you who understand what these terms, it's fine. If you don't, you can write these terms, look on the internet. What is condition number? What is the deblurring? How they done? If you're interested. If you're not interested, no problem. Okay? We continue with this, because I'm not going to talk about this, but if you're familiar, you see all these terms are connected in signal processing. Different applications, they call it slightly different. But They're all related. Okay, so we focus on signal enhancement, only signal enhancement. So we try to estimate or to find x1t, which means that we find x convolved with the impulse response from the source to one of the sensors that we choose. Which sensor will we choose? The one with the least amount of reverberation, obviously. So we will use the other signals in order to estimate this. Inverse transform, what do you mean? The impulse response? Here, I don't need it. I don't know the impulse response. I don't know G1t. I don't know. If I knew that, maybe I can estimate the source. But I don't estimate the source signal. I estimate the source signal as it received in one of the sensors. And we call the sensor that I choose, I call it reference sensor. Because I need, out of M sensors, I need to choose one of the sensor, and I call it the reference sensor. It means that this sensor, for me, if I didn't have noise, the signal that was measured in that sensor, maybe it has less reverberation, maybe it has higher signal to noise ratio. So I start with one of the sensors. You see, with the single sensor, the problem, I cannot choose a reference sensor because I have one. So I take this sensor, I try to suppress the noise. If I have multiple sensors, I can choose the best sensor or to choose arbitrarily. If I think all are the same quality, the signal or the SNR is the same, I will choose arbitrarily one of them. But if they are not the same, I will choose the best sensor, right? So if I choose the best sensor, already I improved the problem, I improved the performance compared to a single sensor, right? Already, by choosing the best sensor, already I did something. But now, not only that, I want to choose the best sensor. If I don't know which one the best sensor, just choose arbitrarily one of them. But suppose that I choose the best sensor, and then I want to use the other sensors to help me reduce the noise in that sensor. Okay? Understand the problem? So, instead of this, I have in the single channel, I will use only Y1. I will use only Y1 to estimate X1, right? For the single channel. In the multi-channel, I use all the measurements from 1 to M in order to estimate X1. So I have more information, more measurements. Okay? So how to do that? So what I do in the time domain, so this is the problem, okay? So now we understand the problem, and we also made some definitions. What is signal enhancement? What is joint signal enhancement and dereverberation or deblurring, whatever you call it? You understand the problem. So now, since we want to estimate only X1, we focus on signal enhancement, and we use all these signals. So what we can do in the time domain, we need to work on certain length of measurements. So what we do for each signal here, each sensor, we choose L samples, L past samples, and then we choose L past samples for each sensor, so we get ML samples Okay? So we have a vector y that instead of length L, just like in the single sensor, now it will contain ML samples, because we take L samples for each sensor and concatenate it into a long vector of ML sensors. Now, instead of estimating one sample at a time, you know, in the single channel, every time we estimated only one sample from the L samples of measurements. Now we can estimate maybe more than one sample, maybe 2 samples, 3 samples. Maybe we can estimate L samples, up to L samples. So actually we define Z, T, with line, whatever. Okay, so we will define. So this would be a vector of length either 1, 2, up to L samples. Okay, so just for the case of, because I don't want to carry all these values all over, I want you to understand, okay? So we worked with one sample also in the single channel. We can work with one sample at a time also for the multi-channel, and the methods will be similar to the single channel, right? Because if I want to estimate just one sample at a time from these ML samples, now that it's a vector of ML, I can work similarly to the single channel. But instead of working with vectors of length L, I will work with vectors of length ML. Will I get a better performance than single channel? Yes. Why? Because if I work with this correlation matrix, the correlation matrix, so it contains much more information. It contains not only correlations between 2 samples within the vector of length L. It contains the correlations between any sample within each vector of length L to any sample of even another vector of length L from another sensor. So all these correlations, they contain a lot of information. But similar to what we did with estimating a single sample from vector of L, we can change the filter. Now the filter, what will be the length of the filter? Okay, so it will be, the length will be a filter of length ML. And so in the single channel, we did something like that. We did H transpose YT. This was the linear filter that we tried to achieve. Remember? So it was like this. This was an estimate. So we can do it also here with the multi-channel. And then the same method that we worked in the single channel, we can do it here, but we will exploit information and correlation between channels. But I don't want to repeat, to say something like that, and then do it again with these vectors. Of course you can do that. But now I want to give you additional methods. So there is another way. Instead of estimating one sample, we can estimate up to L samples. So now, instead of this, I will write our estimate, which is x1 hat. So x1 will be a vector of x1t, x1t minus 1, and so on until x1 t minus L plus 1. So it's a vector of length L. So I try to estimate a full vector from these ML measurements. Of course, in the single channel, it will not work. But in the multi-channels, because I have more than a single channel, I can do that. So, of course, if I estimate only one sample at a time, and the information is reliable, so the performance will be higher, but it's higher computational complexity. The more samples that I try to estimate from this vector, so I reduce the computational complexity because I estimate a whole block of samples from the same information. So the performance will degrade, but I also, the computational complexity will be lower because I don't need to repeat all these computations with the filters for each sample, but I estimate a block and then I estimate another block and so on. By the way, I can also do some overlap and add to average the blocks that I estimate. Also possible, just like with the inverse STFT. Okay, now let's try to simplify things. Okay, so suppose that I want to estimate this using a filter. So now the filter will be a matrix. I can call it H. And the size of H that I multiply with the vector T. Okay, just like this. So what will be the size of H? It will be L by ML, this matrix. You see, because the length of Y is ML samples, because it contains L samples from M sensors, and H is a vector, is an optimal filter of size L by ML, and then we get a block of L samples that we estimate that are related to the samples of the reference sensor. Okay? So maybe it's a lot of information for a short time, but you will see, you will understand all of this gradually. Okay? So even if I put maybe too much information in short time, but let's go through the mathematics and let's see, and you see that it's not that complicated. Okay, so here we have the measurements, and now we take, the first step is to take L samples for each sensor. So we have L noisy samples for each sensor, and then we concatenate them into a long vector of length ML. So YT is defined as taking the L samples from each sensor and concatenate them into a vector of length ML. And it's the same, defined for X and V, for the desired signal and the noise signal. So if in the single channel enhancement we assumed, in order to compute the variance of Rx and the variance of Rv, we assume that we know the correlation between any two samples of the desired signal and any two samples of the noise signal, as long as the length, the distance between the samples, is up to L samples. Now we need to know also the correlations between samples in different sensors. Okay, so it's more information, and if we use more reliable information, we will get better performance. If this more information is unreliable, it will be even worse than a single channel. Okay, so I told you, you need to remember in signal processing and also in life, if you use reliable information, you improve the performance. You improve whatever. If you go to somebody and you ask a question and you get unreliable answer, and you think that it's true, it's worse than not to get this unreliable answer. That's why when you use information, make sure that the information is correct. So if you have more information, covariance matrix or correlation matrix of Y, it's a longer vector. It contains more information. So this matrix, the correlation matrix, is ML by ML. So if you estimate something with more information and it contains wrong values, you will get worse result. Okay, so multi-channel signal enhancement is not necessarily better than single channel if you use information or you make estimation of this correlation matrix that is inaccurate. It's more sensitive. Okay? So, okay. It's more sensitive to false information. But suppose here life is much easier. In this course, we assume that we know this more information reliably, accurately. So here we use the correlation matrix of the vector Y, which is a matrix of ML by ML, large matrix. And we assume that we know each one individually, the correlation matrix of the desired signal and the correlation of the noise. And we assume that the rank of the noise, rank of RV is ML, so it's full rank matrix. And the rank of Rx is smaller, is P, which is smaller than ML. Okay, so you remember that when the rank of Rx is smaller than full rank, we are able to reduce noise even without distorting the signal. This is important, just like MVDR. So we can reduce noise, we can minimize the noise under constraint of distortionless response, which is nice. That's why this is important, that the rank of Rx is smaller than ML, is not full rank. Otherwise, if it's full rank, still we can reduce noise, but necessarily it will come with signal distortion, which is still okay because we can use Wiener or we can reduce noise from the weak signal components. And gradually we will reduce noise from higher and higher, stronger signal components, and we get a good trade-off between noise reduction and signal distortion. But always we will have some trade-off. Okay. Let's continue. Joint diagonalization. So how do we find optimal criteria or performance measures and the optimal filter, which now it's a matrix, it's not a vector. In the single channel it was a vector, but now, because we want to estimate more than a single sample, so it becomes matrix filter. How do we find it? So we need to define performance measures and derivations. I sent you yesterday 2 files. One is about derivation of scalar functions and even non-scalar functions. How to do gradients with respect to a vector and how to do derivations of formulas or expression, mathematical expression with respect to matrices. Okay, so if you didn't have time to read it yesterday, I suggest that you read it and follow it because it's important information. You will use it in signal processing and also in machine learning. And also I sent you another file, okay, which is also useful. So please go and read it because it will be relevant to other topics that you study. Okay, so another useful way to reformulate the problem is to diagonalize these two matrices. It's just like what we did in the single channel. In the single channel, we diagonalized, we used eigenvalue decomposition of Rx. Here we take the Rx and Rv, these two matrices, and because they are symmetric, we can find the matrix T such that both become diagonal. So it diagonalizes two matrices. So if we have two symmetric matrices, one of them is full rank, then we can find a matrix T such that it diagonalizes Rv, which is the full rank, and we get here identity matrix, and it also diagonalizes the other matrix, with a symmetric matrix, and we get here diagonal matrix, but some of the values here will be 0. So we can order them in a decreasing order. Okay? So this is called either joint diagonalization or generalized eigenvalue decomposition. Take a look about the properties, open MATLAB. In MATLAB you have GEIG, generalized eigenvalue decomposition. And it's very useful because it makes things much easier. Okay, and the eigenvectors and eigenvalues are the eigenvectors are the columns in the matrix T, and the eigenvalues. So it's actually the eigenvectors of the matrix Rv minus 1 Rx with some normalization. Okay. Note that if we just diagonalize a certain matrix, we know that that the eigenvalue decomposition, the eigenvectors, are normalized. So the inner product between them, it's 0. But here, it's a full rank. So it's not the same. So there are other properties. So I just want to note that. Okay? So pay attention to that. So it's not a similar properties to diagonalizing a single matrix. And we have properties like this, that if we diagonalize the matrix Rx and Rv, so of course the matrix T also diagonalizes the correlation matrix of the measurements. So we get that. And we also know that this eigenvector, the inner product between the eigenvectors and the signal, any signal, so it's strictly 0 for the eigenvectors with the eigenvalues which are 0, just like what we had with the single channel. You see, so because the first P components of the eigenvectors in the matrix T, they span the signal subspace. So any inner product from P plus 1 to ML, this has to be 0 because the signal is not contained there. Which means that if we, just like what we did with the MVDR, derivation of the MVDR filter. So if we have measurements and we project the measurements into this subspace of the first P eigenvectors, and we don't touch them, and we remove the noise that is present in the noise only space, which is the space that is spanned from with the P plus 1 to the ML eigenvectors, we can remove noise without any distortion. So actually from here you see that we can achieve MVDR filter quite easily. We will work on the mathematical derivation, but you understand it because it's similar to what we did with MVDR in the single channel. Now if we work on the first eigenvectors and we suppress them based on the signal to noise ratio and so on, so we can derive Wiener and other methods of filtering. Any questions? Okay. So then we will define linear filtering just like we defined, and